Hey guys, my name is Ni. I'm from City University of New York. My advisor is Michael Mandel, and today I will talk about our CUNY speech diarization system for the CHiME 6 challenge. So here is the overview of our system. First, we use the beam format as the front end to enhance our audio. So we got the single channel enhanced audio out of the 4-channel microphone array recordings. And then we apply the pre-trained SED model to get the speech segments. And then we extract the X vectors for those segments by using the pre-trained speaker verification model. And then we compute the similarities for all pairs of the X vectors by using PLDA. And after we got the similarity matrix, we applied the spectral clustering on the matrix to find a better embedding representation. And we apply the K-means clustering algorithm on the embedding matrix to get the diarization result. And as we know, there are many overlaps in the CHiME 6 data. So to deal with it, we propose a overlap post-processing step to get the final RTTM output. And in terms of the feature extraction and the decoding stage, we use the same acoustic model and the language model as the baseline system. So in other words, our system belongs to the category A of the track 2. So what is spectral clustering? So imagine if you already have the similarity matrix S by using the PLDA, then the first thing you can do is computing the diagonal matrix D, in which Di is equal to the sum of Sij, where j is from 1 to n, and after that you can compute the matrix L norm, where L norm is equal to the inverse of D times D minus the similarity matrix S. And then we can compute the eigenvalues and the eigenvectors of L norm. And we use the first 4 smallest eigenvalues and the corresponding eigenvectors as the embedding matrix. Why we choose 4? Because in every session there are always 4 speakers talking. And then after we got the embedding matrix, we applied any kind of clustering algorithm to get the diarization result. And in our case, we use the simple K-means clustering algorithm. And however, any kind of clustering-based method has one shortcoming, which is it can't deal with the overlap in the speech. For example, if there are 2 speakers talking at the same time in the frame, the clustering-based method can only assign this frame to 1 speaker instead of 2. So this will cause the unavoidable error. So to deal with this, first we need to label the overlaps for the X vectors. So here we define the parameter called ratio. So if more than the ratio of duration has overlap in the X vector, then we label this X vector to be 1. Otherwise, we label this to be 0. And after we got the labels, we train a logistic regression classifier to classify the overlaps. And in the testing stage, so if we detect the X vector has overlap, then we assign the X vector to the 2 closest speakers instead of 1 in the spectral clustering step. That's the way we deal with the overlap. And here is the visualization of our diarization result and the ground truth reference. So as you can see, the upper 4 rows represent the 4 speakers in the original RTTM reference, and the lower four rows represent the four speakers in our diarization result. So as you can see, even though we consider some overlaps in our prediction, like this part or this part, it looks like there are still many missing speech in our prediction. And the reason is that in the real case, actually there are more than two speakers uh, talking at the same time. So in this case, there are four speakers talking at the same time. So for this frame, we should assign the label to the four, to all four speakers, while in our case, the method could only assign the label to two speakers at most. So in this way, our model could cause some errors. Um, and in order to get a more objective measure, we use the DER as a metric to evaluate our models. So we have three different settings for our system. The first one is we only use the spectral clustering, and we don't consider any overlap. And the second one, we apply the spectral clustering first, and we apply the post-processing the next, and we choose the ratio as 0.5. And the last setting, we use spectral clustering and post-processing, where the ratio is set to 0.67. So uh, as we know, there are two different ground truth references for the diarization. One is generated from the CHiME 5 RTTM, and the second one is generated from the false alignment. So if we don't consider the overlap, which means we only apply the spectral clustering, the two DRs are not quite different. Well, if we consider the overlap, then the DRs are very different. Like the DR with the CHiME 5 reference is much lower than the DR with the false alignment. So that's our finding. And if we compare the three settings, we find that the spectral clustering with post-processing and the ratio is 0.67 got the lowest DER if we use the CHiME 5 as the reference. Well, if we use the false alignment as a reference, the spectral clustering method got the lowest DER. And we also compute the DER for the evaluation set, and we got the same thing, the same finding, like the false alignment reference has much higher DER result than using CHiME 5 reference. And if we compare the three settings, the spectral clustering only got the lowest DER for both references. This means that considering overlap doesn't help improve the diarization performance. But is it true for the speech recognition performance? So we need to verify that. So here we apply the acoustic model and the language model to get the WER result. And we found that the spectral clustering with post-processing and the ratio is set to 0.67 got the lowest WER for both the development set and the evaluation set. So this indicates if you get the best diarization performance, it doesn't mean you get the best word rate performance. So this means the diarization result doesn't match the recognition result. And we also we also compute the word rate for the CHiME5 reference and the force alignment reference, which means we use these two RTTM as the, the input for the decoding. And we found that the force alignment reference got lower word rate for both development set and the evaluation set. And we think that this reference may be better for on the recognition side, but it may not be optimal for the diarization set. So we need to take a deeper analyze on this. So we also visualize these two ground truth references. So the upper four rows represent the four speakers in the CHiME5 reference, and the lower four rows represent the four speakers in the force alignment reference. And we found that there are many more pulses in the force alignment RGTM than in the CHiME5 reference. So the reason is since the force alignment is in the word level, so the duration is actually represent a word. So if the pauses between the words are longer than 300 milliseconds, then we regard it as silence, or you can call it non-speech. However, in the original CHiME5 reference, we just regard it as a speech region. So if your diarization prediction, you regard it as speech here, so your diarization performance won't change so much if you use CHiME5 as a reference. However, if you use the new force alignment RTTM as a reference, and you regard it as speech, then your DER will be much worse. So that's our finding, and we can regard these two references as the upper bound for the category A of the track 2. So so the force alignment reference should be better for recognition, but we need to verify if it is better for the diarization. And here are the references, and that's all. Thank you.